The global potato chip market generates nearly $100 billion a year. That massive economic engine runs on a single, uncompromising consumer demand. Absolute, identical perfection. Whether you buy a bag in Tokyo or a bodega in New York, you expect the exact same weight, shape, crunch, and flavor profile. We demand rigorous mathematical consistency from a product pulled directly out of the dirt. We are expecting a wildly irregular, biologically chaotic tuber to behave like a stamped piece of metal. To manage this, corporations contract millions of acres of farmland across the globe. They dictate the exact agricultural parameters, planting highly specific high-solids potato varieties, engineered for dense starch content and low water retention. The central conflict of the snack industry is logistical, not culinary. It is an ongoing effort to force organic variants into uniform predictability. But that global supply chain is increasingly vulnerable to its environment. Extreme weather, prolonged droughts, and aggressive new crop diseases introduce massive volatility into the system. Farmers attempting to control these highly specified crops are dealing with physical realities that do not care about a production quota. This line chart tracks the direct financial impact of that climate volatility. As severe weather events disrupt planting cycles, the cost of acquiring viable raw potatoes has recently spiked by 23%. For manufacturing plants, a bad yield means they are no longer intaking pristine, uniform potatoes. They are forced to process battered, highly stressed, and highly variable crops. Left unchecked, this level of raw material chaos would destroy the commercial viability of the final product. The variance has to be beaten out of the crop at the factory level. The unpredictable natural world is left at the loading dock. Inside the manufacturing facility, the environment is strictly regulated and heavily mechanized. These industrial lines operate at a massive volume. A single facility can rapidly ingest and process up to 36 tons of raw potatoes every hour. The first biological filtering happens immediately. Samples are test-fried to check their sugar and starch content. Potatoes with excess sugar will chemically react and turn red when fried. Those batches are instantly rejected. What survives is subjected to aggressive mechanical standardization. Rotating high-speed slicers tear through the batch, feeding the slices directly into continuous frying systems that lock in their physical shape. These mechanical steps serve one highly specific purpose: converting thousands of unique individual crops into a single continuous stream of raw material. But cutting and frying isn't enough. To enforce absolute visual and structural perfection, the assembly line hands control over to artificial intelligence. The chips enter the optical sorting phase, traveling across the belts at extreme velocities, up to 4 meters per second. Suspended above and below this fast-moving stream are multispectral cameras. Operating at 100 frames per second, they capture high-resolution imagery of every angle of every chip. This data feeds a computational matrix. The AI makes 5,000 decisions per second, scanning for microscopic defects. Sort-to-grade software calculates which variations are permissible and which dark spot or tear critically violates the specification. When a failure is detected, the execution is physical and instant. Matrices of tiny air jets fire a targeted burst of compressed air, ejecting the bad chip out of the stream in under 30 milliseconds. At this precise moment in the factory, the chaotic reality of agriculture is entirely replaced by uncompromising mathematical certainty. The chips are now uniform, fried in high oleic oil, and perfectly seasoned. But the moment they are finished, atmospheric decay begins. This diagram shows the final defense mechanism, the bag. It is a composite metallized BOPP film built from multiple distinct layers. These combined plastics and a microscopic aluminum coating form a highly specific barrier, blocking external moisture, light, and ambient oxygen. Before sealing, the bagging machine executes a nitrogen flush. It injects a targeted puff of pure nitrogen gas, completely displacing the ambient oxygen. This chemical technique, known as modified atmosphere packaging, effectively pauses time. Without oxygen trapped inside, the oils cannot oxidize and the chip will not go stale. That bag of chips on the shelf represents the convergence of global agriculture, artificial intelligence, and material science. It is the product of using high-precision engineering to hold back the biological reality of decay.